Fantastic. Thank you very much for having me. So, yeah, this is a topic I love to talk about. I could talk forever, but I have to compress everything into a reasonable time. But feel free to ask me any questions you want afterwards. I'm an engineer. I'm a diehard engineer. Slaughter fumes make me happy, and no, it's a good thing. So there's going to be a heavy engineering aspect to this, but I think it's great because I'm going to talk about not why we're doing it and what our ultimate technical goals are, but mistakes I made and things we did along the way. And I think there's probably a lot more you can take from that. And even though some of these may be engineering specific, you can certainly apply these concepts to business and entrepreneurship in general. So there are two ideas that are really inspiring or informing what I do. One is what I think of as the rise of the nano air vehicle platform. And everyone here knows what a drone is. And typically when you think of a drone, you think of like a DJI Phantom or something about this size. And I argue that actually the trend is getting towards smaller and smaller and smaller drones. And I wouldn't be surprised if the median drone, or the average drone, is more like that than one of these larger ones. And there are all sorts of advantages you have when you get to drones of a much smaller size. They're stealthy, they're light, you can transport them. If they bump into you, no big deal, no damage. And because they're small, they can get into tight spaces that you wouldn't be able to get otherwise. So that's one thing. And right now, there are really two ranges. You either have militarized platforms like the Proxdynamics platform. They're made in Norway. The founder's a genius, good guy. $150,000 for a system. They weigh about half an ounce. At the other end, you have this toy platform for $15, which you can buy from Amazon. I have several of them. They're wonderful devices. But you notice there's 4 orders of magnitude difference in terms of price. It's just interesting observation. But the second item that is inspiring me is what I think of as the importance of near-Earth autonomy. It is easy to have your drone fly high above the ground, away from obstacles. You can use GPS, and there's not much up there to bump into, unless you start thinking about other aircraft. But it's a fairly easy problem, in my opinion. What we want to do is to descend and fly down amidst buildings, avoid trees, fly into a building and see what's going on inside. And you can think of obvious military applications for this. There are tons of civilian as well, search and rescue, scouting out a building for a fire, all sorts of possibilities. Even smart agriculture. You want to look at a certain tree, you can fly up close, which you wouldn't be able to with a much larger platform. But the near-Earth environment is tough. You have obstacles everywhere. There's a lot of turbulence, light levels can vary, and GPS, if you have it, it's not really accurate enough. And we all think of GPS as this wonderful thing, it tells us where to go. But if you're trying to fly in an environment like this, maybe GPS will tell you where you are, but unless you know where this tree is, you're not going to be able to avoid it because you just don't have that information. So we want to be able to provide some sort of sensing to the platform, to the drone, so that it can figure out on its own whether it's about ready to bump into something. And this is where we are right now. And at the end of the talk, I'm actually going to fly these around. This is one of our little platforms. It's built upon basically an open source project. We just added a bunch of our own electronics. There are an array of 4 stereo cameras, 8 cameras on this. And when it's properly set up, you can fly it around. It hovers. You try to fly it into something. It bounces away. And we're having some nice progress with this. But of course, we're fitting it into a small size like this. And how do we get something into this small size? Well, let's back up a bit and talk about vision. We want our drone to be able to see objects. Let's talk about eyes. The human eye has around 100 million photoreceptors. And a photoreceptor is sort of a biological equivalent of a pixel, a little circuit that senses light. So about 100 million in your eye. Your iPhone has maybe 10 million pixels. And you notice that this is actually not that far from that in a geometric sense. But look at flying insects. A dragonfly has around 30,000 or so photoreceptors. A fruit fly has 800 pixels. If someone said, here's your new iPhone has an 800 pixel image sensor, you'd say, no, I'm not interested. Yeah, you would laugh. But this is what fruit flies, these dragonflies are able to do things with, and they've lived for hundreds of millions, I don't know how many hundreds of millions of years, but they've been around for a long time, so obviously it's working for them. And this is why we're inspired. I mean, dragonflies are maneuverable. They're agile fighters. They're predators. They hunt down other insects and eat them. And they avoid each other. It's just fantastic. But how do you do this in such a tiny brain? And this is what has inspired scientists to try to figure this out. And then this inspires engineers like me to say, okay, let's build it. I mean, if we can build it, then we really understand what's going on. So, again, scientists have done a lot to study the visual system of the fly. We all know about the compound eye structure, and all the flies have. Basically, an array of lenses that respond to light. And there are a number of neural circuits that have been mapped out to a large extent. And in a flying insect, by the way, the majority of the brain is actually allocated toward visual processing. That's how important it is for insects. But scientists understand what's going on. And one thing that has been studied a lot is the fact that some of the neural circuits in a fly's eye respond to visual motion. Visual motion as an optical flow. And this is, now moving from engineering to psychology, optical flow is a phenomenon that you have all experienced. You can define it as the relative motion you see as you're moving throughout the environment. So imagine yourself an insect or a drone. You're traveling forward. The whole world appears to expand from in front of you, flow around you, and compress behind you. If you look down, you're traveling forward, you see the ground move backwards. The closer you are to the ground, the faster the optical flow. If you're about ready to bump into something, you see a rapid expansion. And if you can measure the optical flow, you can perceive aspects of the environment. And that's intriguing. Scientists have figured this out. Computer scientists have figured out how to do some of this. And insects, it appears, rely upon this a lot. In fact, it appears that insects use elegant stratagems, if you will, basically heuristics or rules or reflexes that respond to an optical flow pattern to do something. I mean, these are very, very intuitive. If you want to avoid collisions with objects, turn away from a region with a lot of optical flow, right? If you're about ready to walk into something that doesn't appear to move fast or appear to expand. If you want to go down the center of a tunnel, keep the optical flow on your left and right sides equal to each other. And some scientists in Australia figured out that this is actually how honeybees are able to fly down the center of a corridor. They actually equalize the left and the right optical flows. The way they did that was to train the bees to fly down a laboratory tunnel, and one of the walls was shifting at a constant rate. And so then the bees would shift their positions to achieve the illusion of the left and the right sides being equal. It's just a fantastic heuristic. And by the way, you do it too. So pay attention. Next time you walk down a hallway, all right, look at your left and right optical flows and see what you do. My favorite, of course, is if you want to hover in place, just keep the optical flow zero everywhere. It's very intuitive, right? If the roll is not moving, it doesn't appear to be moving visually, it means you're staying in one location. Now, if you ever go hiking, and if you live in this part of Virginia and you don't go hiking, shame on you. It is a beautiful area, by the way. You may have noticed insects or bees or flying near a cluster of flowers, and a gust of wind comes along, and the cluster of flowers waves a bit in the wind. And the insect will actually fly lockstep with them. What the insect is doing is basically visually locking on to the visual pattern of the flowers and the branches. That's actually what's happening. You could actually take these insects and stick them in a rotating chamber and rotate the chamber, and they'll actually move. In the same way that if you're in a IMAX theater and everything is the projection is showing motion, you get dizzy. So okay, fine. This is interesting stuff, but how do we turn it into reality?
So can I
Yes.
ask a quick question?
Yes.
So when that last slide is just it's amazing on a number of different levels. It's amazingly obvious after you've explained it.
Yes.
And you mentioned psychology, and you mentioned this is also has to do with obviously physiology and everything. When you come up with this stuff as an engineer, how much are you working with those other people in terms of getting this explanation?
Actually, a fair amount.
scientists in
So
other
it's
areas?
actually a good question. So I do attend meetings where you have biologists, engineers, and these are fascinating meetings or conferences.
Yeah.
But again, I mean, I'll actually, as I go through this later on, you'll see to address the question of, okay, how do we take these concepts and turn them into reality?
Right.
And it's not always as easy as you might think, or it's not as
Yeah.
straightforward. There are tricks along the way. But yeah, definitely. We talk with them, we get ideas, and we share ideas. Just to give you an overview, this is, I have to say why, if I'm going to say why we're so good, I have to say what everyone else is doing. So this is the typical approach to near-Earth autonomy. You take a large drone, you put cameras, sonar, laser rangers, and all this stuff. You basically tie it together with software, and you can actually get somewhere with this, even with Moore's law advancing. In my opinion, this is not the best approach. That platform is still a little bit big. It would scare me if it were coming toward me. But they're making progress. But there's an argument that, hey, Moore's law is advancing. We just wait 2 years and computers will be fast enough to do everything. And I'd say no, actually, Moore's law is slowing down. In many ways, it's good news because for us engineers, it means now we actually can be creative and make a difference rather than just waiting 2 years for Moore's law to do it for us. So our approach, again, you can think of this as your image processing stack or your information processing stack. Light from the environment goes through a lens, focuses onto a camera chip. A circuit board operates the camera chip, grabs images from it, does image processing, and then there are other control algorithms that control the drone, and there you go. And again, you can take a bunch of off-the-shelf components and put them together. And I'd say this is suboptimal. The reason is that these components were not necessarily designed to work with each other, and they weren't necessarily designed for drones. They were designed for other applications. So the approach I take is what I call the vertically integrated approach. It's a bit different. We design our own optics. We design our own camera chips. We actually design our own chips. I don't have a $10 billion fab. I'd love to have one, so we have someone else do that. But we design our own boards, we design our own algorithms, and an interesting thing happens when the same group of minds does all this at once. We learn how to optimize, we can control the interface between the different layers. We can make it easy for us to use, instead of being constrained to some standard that everyone else forces upon us. We can identify what's important, augment it, and this is my favorite, we can identify what is not important and get rid of it. That's very important. We want to get rid of things that are not, and that's why we can get small. Getting a bit more into the engineering aspect, this is sort of a model for one of our vision sensors. And the idea is that you have a vision chip. It's basically a camera chip that has pixel circuits on it to grab an image. But then there's also circuitry, analog circuitry on the vision chip to do some image processing using analog electronics. And there's some interesting operations you can do. I'll explain one briefly. So what comes out of the vision chip is not just a raw image, but a partially processed image. And then on the back end, we have an off-the-shelf processor, a microcontroller, or something else. And this runs whatever motion sensing algorithms and other higher-level algorithms and generates an output. And this is a model that we have followed really for about 15 years. And what's changed over the years really is how we do this, and how much do we put on the chip, how much do we put on the processor. So this is hardcore engineering here. This is an example of one motion sensing algorithm we came up with a long time ago. And you can imagine here an array of pixel circuits, right? These would be on the focal plane, a lens would focus light onto these pixel circuits and they would respond. Let's suppose you had an edge, like a vertical edge, a shadow, so that this pixel was in the shadow and dark, photoreceptor is in the light, and those would get fed to what is called a differential amplifier. A differential amplifier is a circuit that looks at two inputs, computes the difference, multiplies the difference, and gives that as an output. So in this case, if this differential amplifier had the dark photoreceptor here, the negative input, the bright photoreceptor, the positive input, this gives a high value. And we just have an array of these staggered to basically effectively perform what's called a mathematical convolution of this type of pattern onto the visual field. And then we have other, and so if you wave texture across the photoreceptors, you get a pattern, a set of patterns like this curve, and they're a bit offset in time because the texture reaches one of these before it reaches the other ones. Then we have what's called a winner-take-all circuit. It looks at the analog signals, decides, figures out which one has the highest value, and sets that corresponding output to a digital high, the rest to a digital low. You know, who's the winner? The winner gets the prize. The winner gets to be a 1. Everyone else, you're stuck at a 0. So you get a pattern like this, you know, this 1, 2, 3, 4, 1, 2, 3, 4 type of pattern. And that's something that is actually easy for computer scientists to extract motion from. Just to give you an idea of where we were about 10 years ago, our thinking. So we actually flew it. This is one of our first flights using less than 100 pixels. You can hear the sensor doing things. There's one optical flow sensor on the wing of the aircraft looking down. So if the aircraft is getting closer to the ground, the optical flow is faster. It says, okay, I need to give it more throttle or take the elevator and make it pitch up. Simple proportional control. And it worked beautifully. So the human would be steering, in this case it was me, would be steering the aircraft by changing the rudder, whereas the sensor itself was controlling the height. Very simple demonstration. Again, using less than 100 pixels. So we said, okay, let's make 3 of these and stick them on the front so we can try to make our aircraft turn away from a tree or some other object. And this is what happened. It detected the tree, right? You know, here's this nice spike in the optical flow right before it hits the tree. Here's the rudder saying, okay, I gotta start turning. And here's the gyro saying, oops, I crashed. So okay, what's going on here? This is, again, it's just funny when you think about it now. Now, if you go back and look at how insects do different things, this is an experiment done by a colleague, Michael Dickinson. He's I think at Caltech now. And he would have fruit flies fly around a chamber about 1 meter in diameter and have cameras looking in to see what their typical flight path is. They would actually fly a straight line, and when they got close to something, they would make a rapid turn, called a saccade, and fly in a new direction until it saw something else, make a rapid saccade. A bit like a Roomba, if you think about it, when it bumps into a wall, but the bumpers are visual. But if you look at it, they turn very tight. It's a very tight turn. And that got me thinking, you know, could we mathematically evaluate an environment? Let's let D be the typical size of an object, maybe the diameter of an obstacle, the diameter of an opening that you have to fly through, or the distance to which you're going to approach something. D is a distance measurement. Let's let R be your aircraft's turning radius. That's a first order approximation or measurement of how maneuverable your aircraft is. If R is small, it can turn on a dime, like a sports car. You know, a sports car has a smaller turning radius than a truck. So D over R then is a ratio that defines how large the object is, not relative to a measuring stick, but relative to how maneuverable you are. If you're very maneuverable, you can get very close to something before you have to turn and avoid it. And that's what insects are doing. They can turn on a dime, literally. That's why they can fly around this environment. Whereas that heavy airplane I was flying earlier has a turning radius of maybe 50 meters, 30 meters, something like that. So that means to get the same D over R as those fruit flies, we have to be avoiding mountains, not trees. Very interesting. So how do we get it to work? Easy. Make the aircraft more maneuverable. And this is what happens, by the way, when an electrical engineer designs an aircraft. It's yes, that's masking tape. Masking tape, glue, Velcro, duct tape, you name it, it works beautifully. Basically, we stripped out everything that was unnecessary. We took out the telemetry. We made it so that when you released it, it was on its own. Good luck. We gave it a giant rudder so it would turn. What we sacrificed was endurance. It wouldn't fly very long. And we also sacrificed how seriously aeronautical engineers would take that on. But that's okay, it flew. So the very first time, initially, this is kind of what happened. See, it worked. No, and this is a point. It's kind of interesting. You know, for grading systems, you know, A, B, C, D, F. Some places you get a plus or a minus. And this type of work, real life, is basically pass, no credit. Not pass, fail, just pass, no credit. If it didn't work, you just get no credit, you try again. And usually it's no credit. You have to do a lot of no credits before you pass. And that's what it's like. You have to try things and try things and try things and make adjustments, and then you get to work. So this is one of the very first times it worked, and it was still not working quite right. But look at it, isn't that beautiful? It just sort of zagged around. It looks like an insect in a way. It turned away from the trees, and then it turned back toward them again, and then it escaped. So when we actually tuned it a bit better, okay, and then the throttle cuts off. We learned that if you don't cut the throttle off, it will fly away. I have a funny video of that. On the right is, yeah, it's really funny. Yeah, it turned and avoided once. This one actually avoids 4 times before it lands. And you notice that this actually doesn't look as exciting as this. It's one interesting thing about robotics. When it works well, it's actually kind of boring. It's most exciting when it's almost working or when it's barely working.
Hitting trees.
Yeah, hitting trees. Yeah, I was scared. It was high. I was like, oh gosh, it better not crash. You can use, you can use like a crescent wrench and rope and fling it up there and hope the police don't. Anyway, so let's not talk about the police. Okay, so the first lesson is, if you want to get something to work, sometimes you have to optimize the system, not just optimize a component. We got this to work not by working on the sensor, but by making the aircraft more maneuverable. Very, interesting thing. So, very good. What do we do next? Well, let's make it better. Let's make it bigger and better. We add more pixels. We put some additional circuitry so we can do more things, more binarization, more stuff, more sophisticated, more powerful processor. Lovely board. Here's the chip. Actually, I should have around here a circuit board with some exposed chips so you can see what they look like. And here we are. Here is an RC car driving down a tunnel. Left and right optical flow. Keep the left and right optical flow the same. And it's driving pretty fast. That's not time, that's the actual speed. Later on, we added even more features. Look. Multiple layers of features, and then we added a parallel processor onto the chip. It has one instruction: compute optical flow. Very powerful chip. That took about, I think, 5 months to design. And we said, hey, we can put a bunch of these cameras onto a soccer ball shaped type of thing, stitch the imagery together, have an omnidirectional field of view, so we can measure omnidirectional optical flow at 500 hertz. Works great. So then we decided to fly it, and here's what happened. I'll just show these 2 videos at once. The top shows the helicopter hovering in place, barely using 6 sensors, and here's a helicopter turning away. See, we built it and everything worked just fine, right? Okay. Was it that easy? Yes or no?
No.
Everyone's saying no. Good. Now, here's what really happened. What really happened is we built a ray tracing simulator, basically using a video game type of engine, OpenGL. It's software to do high-speed rendering. And we had a whole virtual simulation where you can have a simulated aircraft fly through a simulated environment. We had other code that simulated how the sensors would operate to close the whole loop. And it didn't work in the simulation. Usually you say, hey, work in the simulation. We can go home now. Obviously you get it to work in a simulation, and then you try to get it to work in real life. If it doesn't work in a simulation, we're toast. And that's what happened. I realized this was not going to work. I invested all this time. Who here knows the 80-20 principle or the 80-20 rule? Who's heard of it? If you're an entrepreneur, you have to know this rule. You have to know this rule. Right. 80% of the value, this is an anecdotal rule. It's not a hard rule, but it's anecdotal. 80% of the value comes from 20% of the input. If you manage a stock market portfolio, 80% of your returns come from probably 20% of your investments. 80% of your profit probably comes from 20% of your customers, or 20% of your products. 80% of the failures of a system come from 20% of the failure causes. It doesn't have to be 80-20, it could be 90-10, 99-1, some other, they don't have to add up to 100, but really what it means is that the majority of the benefit you get comes from really a small minority of the things. So I was thinking, okay, I made a list of all the different features that describe the system, describe, that could have contributed to it working, or that I think of as advantages. Just a list. Number of pixels. Was it the fact that we had these certain types of circuits on the chip? Was it the lens? All these different things. And I asked myself, okay, if I were to do this over again, but with a bit more wisdom, and to pick just 2 or 3 of these features and focus on optimizing those, could I get to work with just those features? Force yourself to ask that question. Not that I'm going to eliminate them all, but if I had to do it with just a few, which ones would I do it with? And I realized it was actually just a few of these. Keeping the number of pixels small, having a high frame rate because your vehicle is flying around, so you want to be able to grab imagery at a high rate, and not the type of optical flow algorithms, but the fact that we had tuned them just right. We had the right threshold to avoid something. We had the right time constants to make it just the right, fast enough, not too fast, not too slow, that sort of thing. And that was what was most important. So here's our lovely sensor architecture. This is what we did. We just ignored them. We didn't refabricate the chip. We just ignored them. We read out this information here and used this processor to emulate a simpler device, emulate a simpler image sensor. And that's how we got it to work. It's a very, humiliating thing because you can invest a lot of effort into trying to get something to work, and you realize, wait a second, this is what was needed. But what this means is beware of feature creep. I want to say feature creep is expletive, but that would be impolite. But yeah, feature creep is something that you need to avoid. Try to avoid expanding things too quickly, and occasionally do an 80-20 analysis to say, okay, do we really need all these things? Is this more important than that? You have to think about that, because every time you add a new feature, you really increase the complexity of the system, and you can do it to the point where it's actually more costly to include the feature than the benefit that feature provides. So, I'm starting to learn here. We're starting to actually do things occasionally right. Let's apply some new lessons, and this is actually getting toward where we are right now. Another biological principle: can we make this little helicopter hover in place and do things? And again, going back to the neurobiology, it turns out that they're called tangential cells inside of a fly's brain, and they're little neurons that respond to global optical flow patterns. So if the insect is going up, there's one neuron that will tend to fire a lot and respond to that. If you're rotating along an axis, another neuron would tend to respond to that. And one biologist figured this out by strapping down these poor flies, giving them a little virtual reality of like little optical flow here. Okay, does this neuron fire? Okay, put the optical flow here. When does this neuron fire? And replicate this whole thing. And so that's the principle. We can abstract a bit mathematically, and we have these simple rules. Again, if you're going up, the optical flow everywhere is going down. If you're going forward, the optical flow is a bit like a sine wave. Here's why it's like a sine wave. You're traveling forward, 0 degrees, 0 optical flow. 90 degrees, optical flow is backwards, it's flat positive. Behind you, 0 to the left, the optical flow is actually going to the right instead of the left, which is negative. 0 positive, 0 negative, that's a sine wave. You can do these Fourier series-based decompositions that extract how the platform is moving. We implemented it using 8 cameras. There's this is just 8 cameras mounted on a ring looking in different directions. This is another version of the thing. Believe it or not, this didn't work as well. I won't get into that. It sensed more, but it actually upset the stability, the mechanical stability. We made a new vision chip, again with other types of circuits that were more oriented toward allowing us to reduce the number of pixels electronically. So even though this was a 64 by 64 array, that image could be put onto this square here, which is an array of capacitors, and then we can, using analog circuits, turn that into a 32 by 32, or a 16 by 16, or 1 by 64. We can do all those things. We made changes to the interface, and by the way, this is not rocket science. I don't know if rocket science is a metaphor anymore, but this is not that may sound so funny. This is not rocket science. So, We actually even put the connections to the chip all on one side, so we can mount the chip right here, have this simple circuit board, make connections, and have one processor operate all those chips at once. These are just things we realized this is a way to make it better. We did a lot of hardware hacking. And again, this is an example of how electronically we can take that 64 by 64 array of pixels and generate just 32 pixels vertical, 32 pixels horizontal. This is for measuring vertical optical flow. This is for measuring horizontal optical flow. And it actually, this system works pretty well. So here's an example. The helicopter is holding its position using vision. When he pulls it down, it says, oh, I saw that move down. I better increase the throttle, go back up. And it goes back to reverse it. Move it up, move it down, move it left, move it right. It worked pretty well. And that platform, we got 6 minutes of flight. You could even just set it up there and leave it there, and it'll fly for 6 minutes. And when the battery dies, it lands. Very nice. And we even found you could do this in the dark. We put little LEDs on the helicopter. They provide illumination. So here, with about 1,000 pixels. And again, these are pixels after we electronically downsample them. So it's just interesting to learn. But we did a bunch of experiments, and this is sort of an example of how many pixels did we need to avoid a large object, avoid a cable, hover in place. On the order, we needed really hundreds of pixels, which is similar to the resolution of most insects, as opposed to a megapixel camera. It's very, and just to show you how low can we go. 8 pixels, it's controlling its yaw angle. Turn this down here. You can see control is not on, then the stabilization is turned on, and it's just using one sensor with only 8 pixels looking forward, and if it sees that's moving, it tries to adjust the rotation to 0. So yeah, even 8 pixels you can do things with, not 8 million.
So is does that decrease the cost? Is that why we're trying so hard to reduce the pixel?
Oh, all sorts of, there are actually all sorts of reasons. Part of the reason it's reducing costs, it's reducing overall system complexity, it's making it faster. And again, if you're grabbing more pixels than you need, you're actually grabbing a lot more information than you need. If it slows you down, you have to have a heavier processor. So it's just all out collectively taking all these different things together to make the system as light as possible. So one more anecdotal rule. I love this. The 80-20 principle. Okay, let's suppose, since this is a venture club, you have your start venture, and over a year you collect a bunch of data, you have a bunch of different customers, and you analyze, okay, each customer brought me this much revenue. Some customers will bring you a lot of revenue, some customers will bring you very little bit. And if you take all that and rank it, you'll get a curve pretty much like this. It's called Zipf's law. And this curve very often will follow not exactly, again, this is anecdotal, not hard physics. A curve very much like this. The value will be basically some constant multiplied by the rank, 1, 2, 3, 4, to say the -1 power. It could be -0.95, -1.1, and so forth. I mean, do this sometime. Go on Wikipedia and look for, instead of it, look at, say, the populations of different cities. The 5th most populated city of a country will very often have twice as many people as the 10th most populated city. Not exactly, but it's just, try it out. Your mind will be blown away. What this means is, again, if you look at it from 80-20 standpoint, again, the vital few will give you most of the benefit. You can take that top 20%, divide up again. 4% gives you 64%. And again, 1% gives you half, or something along these lines. It's just amazing how powerful that is. From the standpoint of an engineer trying to take ideas from biology and do something, what this means is that rather than trying to copy all of the ideas, try to first figure out what are the most valuable ideas, the most valuable insights. Even better, try to extract some basic principle from those insights and focus on implementing those rather than copying everything. And this is from an engineering perspective. From a business perspective, I'm sure you can apply that basic metaphor in a bunch of different ways. It's very important you do this, because if you don't do that, someone else will. So getting back to where we are, this is the platform. So in a few minutes, I'm going to attach a battery to it, fly it around, and I'm curious if any of you have any questions first.